Let's start on TCP/IP socket programming phase 1. Here we'll be covering on basic of networking OSI model and overview of TCP/IP internals. And this is phase 1 as the first slide says. And we can the next phase 2 I will be covering the socket programming. So let's start on this. Okay, so if you look at the OSI, the first diagram is like OSI model versus TCP/IP model. So OSI model is something which we call theory, and TCP/IP model what's commonly used right now across all internet architectures. And you can see why OSI model has been designed in this way, like where you have like physical layer, data link, network, transport, session, presentation, applications. So you see like each and every layer is distinct, and they're doing in terms of how they are transporting data from applications to a physical layer. Where you will get different address identification, like you have a network layer, like which we call IPv4, IPv6, then we call TCP transport layer, which is your TCP, UDP, and they have something called port identification. And then you have session layer and presentation, which will have different kind of handle which application can use to use that applications, and like across different states. When I say states, it means like like different handles, like just to identify. And states like maybe multiple threads, maybe in multiple contexts the same handle may be used to reuse the same applications. So we will be understanding more if we go further, but here what we need to focus more on is how this networking layer works. So if I talk more about the what's written here is like device driven hardware. So what I mean to say in the context of networking is that it is the TCP, that's our layer 2, the data link layer and physical layer. That's what I mean should be covered by the device driver in the networking context. So like Wi-Fi driver or internet driver or Bluetooth driver, they should be termed as a device driver here in the networking context. And those the APIs from those device drivers will be used by their IP layers and TCP layer, transport layers and application layers to receive the packet and to transmit the packet across the network. And there's some different acronyms, some different architectures. So I have taken the diagram from a book which I can share later on which book, but yeah, we will not go on this. And I'll just like to cover a bit also on user process and kernel process. So you see like all this device driver and TCP/IP, like mainly in the context of Linux kernel. If you see the whole TCP/IP stack is in the kernel space, and then on the application layer you have different application like HTTP application, a browsing application, or say any Skype on Android, right? So they are called application layer. They are user processes, and underneath they talk to the kernel. And not all form factors have this kind of model like user process and kernel process, but at least any Linux laptop that you have, or you say any Android device that you have, right, they have a concept of user process and kernel process, and where the user process talks to kernel via some, like I haven't shown here in diagram, like some socket APIs, and talk to internally to TCP layer, IP layer, and ultimately transmits a packet and receives the packet. So this let me clarify more if you go further in the diagram right now. So this is what I talked about, and we should really look at why the networking TCP/IP is required here. Really, we want to connect the billion of devices across the planet, and that's what we're talking about nowadays, is Internet of Things. And then we also cover device driver, user process, kernel process. Let's go to next slide. The TCP/IP protocol suite. So again, you can see that I was showing there the TCP, UDP, and IPv4, IPv6. So these are the layers which are prominent in a networking model, which ultimately carries your data distinctively, and all other protocols out here like ARP, like address resolution protocol, or say IGMP or ICMP, right? IGMP is like internet group multicast protocol, like for video conferencing. This protocol is used, like when I say video conference, I say one to many kind of communication where you want to multicast a packet. Then ICMP protocol is used, where each node is made a part of a group, and anybody sending to that group goes to all the hosts which are part of that group. So that's what ICMP protocol is used for. And then you have ICMP, which is Internet Control Message Protocol. So again, this is for debugging the internet, for congestion notification, or say for debugging the network, like pinging and trace routing, like finding on the routes on the network. So all that is used, all that is developed using the ICMP protocol. And then anyway, you know about layer 2, and so all this HTTP, FTP, SMTP, if you see, they are using TCP, and DNS, WEP, SNMP, they are using the UDP protocol. So there are different applications which some are using TCP, some are using UDP, and the decision is based on what application wants to do. Like in HTTP case, they want to maintain a reliable connection, where you say the server, you access a website, and then server gives you the web server gives you the web page data, right? So you want to make sure that all the server data is intact and comes to me, so that I can see the full web page which the web server designer has designed, right? And so same in the case of FTP and SMTP also, because you want to receive the complete mail, like for mail kind of application, SMTP is used. For FTP is like file transfer protocol, which is again a file transfer. So you want to receive the complete file, so your TCP is required. DNS is kind of, you just want to say that, okay, I want to know the IP address of ndtv.com. So you say a URL, uniform resource locator, that you call it, that what you enter into your web page, and then ultimately is also UDP systems make UDP packet and sends to IPv4 or IPv6, and then you get the IP address of that DNS server like ndtv.com, and then ultimately a HTTP browser makes a TCP packet to that ndtv.com IP address, and then you get a web page on your computer. So this is in a concept. Let's go to the next slide. So again, I explain all these protocols out here. So something which I have not explained, like IPv6 and IPv4, you can understand IPv6 is more extended version of IPv4, where the addressing capability was 32-bit address in IPv4. Now it has become 128-bit. Hence, like billion of devices across the planet looks addressable, so that, yeah, they can even connect using the addresses. Otherwise, with 32-bit address, it wasn't possible. And then you have like all I covered, like DNS also I covered, but yeah, DHCP v4 v6 is like dynamic host configuration protocol, which used for assigning the IP addresses and many other parameters, allowing zero conflict networking. Like you scan a network, and then you get all your IP addresses and all your DNS servers configured on your phone or on your laptop. That's what you call zero conflict networking. Now, there's a more advanced concept, but something which I missed to explain here is like TCP and UDP, like which is connection oriented and connectionless protocol. So UDP, you don't need to make a connection, but in TCP you need to establish a connection before you transmit the data. So, and even when you say you need to make a connection, it's not like you make a physical circuit, you make a logical circuit in terms of reserving the buffers based on some identification, like which the source port, destination port, and source IP address and destination IP address. Together they call it a tuple. So you have a source tuple, and you have sorry, not a source tuple, like you maintain a tuple, and corresponding to tuple you maintain the buffers for sending and for receiving. And same way, the UDP is just like a connectionist protocol. So you just want, like you want to just you are doing a web call, so the control messaging happens on TCP, but all this audio data or video data goes over UDP. So I will not say video data, but audio data all it goes on UDP. So let's understand about the next slide right now. So this what you can see right now is the how the internet architecture looks like. Like you have router in between, and then the packet goes from one application, like one process, to another process, and then in router you just deal with till IP layer, but in end-to-end host you deal from applications to transport and all the layers, and to the other endpoint you deal with all that link layer, internet layer, transport and application layer. So routers are just up to IP layer. That's very important concept to know. And then anyway you have layer 2 out here, so nothing much on this slide. We'll go on to the next slide right now. So this is the TCP IP header, TCP header that I'm going to explain you right now. So hope till now the concepts would be clear. Otherwise you can refer back to my slides again. So if you look at the TCP header, it has like a combination of source port and destination port, and sequence number and acknowledgement number. So source port and destination port, anyway I covered earlier also, like for HTTP you have port 80, for FTP you have port 20 as a destination port, and source port can vary, so the system decides which port to be used, and this make a tuple, like one part of tuple like ports numbers, and then also I'll cover the IP header, then you will see the source IP addresses and destination IP addresses. And these two numbers, sequence number, acknowledgement number, you need to understand that why they are used, because TCP is a byte stream protocol, so you want to count each and every byte, so all that is like each and every byte is numbered, and that's what we that's with this fill we track each and every byte sequence number, and acknowledgement number, like how many bytes has been acknowledged by the receiving end, that what we get in this packet, and vice versa, when this is sending a packet, it is also acknowledging how many bytes have been received by received from the other end to this end, right? And then we also go ahead on offset and TCP flags parameter right now. So offset is something that is just telling you the data length, which is on what could be this header size, after this which you will have data to access. Like that's the way programming is done, like you put a pointer till here, and then you reach to this, because all these fields are like of fixed length, you can reach this offset value, and based on that what would be the header size. Like it comes fixed, like you can see 20 bytes, but with the options it may vary, and then so you calculate from here, like this 4-bit number, so you get here what may be the length of this field which the source must be filling up, and then based on that you just do pointer, and as you do in C programming, that you do C plus like pointer arithmetic, the pointer plus the offset value, and these to the TCP data which are being carried over in that TCP parent. And TCP flags, if you see, TCP flags are nothing but like the combination of 6 or 8 these flags. These 6 are very important, like you have send, you have fin, you have reset, push, act, urgent. ECN is explicit condition notification, which I'll not be covering much here, except that yes, used to inform to the source, and especially that the congestion has occurred on the network when the packet comes back. like when the packet is received. But rest, like SYN, is like to establish that TCP session, you need to use SYN. So at the moment you learn in socket programming, like when we do a connect, the first packet which goes is a SYN packet, and then when the connection is closed, then the FIN packet is being sent. The FIN flags will be marked in that packet when this session, when suppose the source end want to close the session, on the other end it has to mark this flag as f equal to 1 here, and then this packet will be called a FIN packet. So if I mark A also here, then it will be FINAC packet, FIN plus ACK. So you will see SYN, SYN. So in similar way, you will see SYN, SYNAC, and ACK when a connection, when a socket call a connect, and the server accept that packet. So a SYN, SYNAC, and ACK happens, which I will show you in a diagram in the further slides. So also you need to cover the window fill here. Window fill is something like how much data you want to send to the other end till the other end says no, I cannot receive any more packet, let me clear out all the packet. So you know, given this different kind of platforms, like where you have phone, where you have a laptop, you have your data servers, so everybody every form factor has different capabilities, and based on that they like one can send the packet faster, like laptop or your data servers, but your smartphone cannot receive packet at that much speed. So the servers, so that's why the window parameter is very useful in understanding that it defines it, like this 16-bit length, it defines how many packets like other end should like I should send before I should get an ACK. Okay, so like I have just like bumped this packet, and if I don't get ACK, it's fine, but I'll bump this packet until all the bump counter has been reached. I will stop. Now I will wait for that. I will wait for the ACK. So that's what window fill means here is, and so as I said, it is 16-bit in length, and which defines like this around 64K kind of window bytes, right? So like but not you know, like we cannot put it is a 64K because the receiving end may not accept that much. No, you will need to put a very big buffer, and that may not be acceptable, and generally it's not acceptable. So normally it is around some smaller value, like I think which I have seen like 2K, 3K, or the 16K max, but not more than that, I think, in most of the sessions. Okay, but I missed that right now. Also the checksum fill, which actually is explaining is just doing a checksum of the header plus data. So when I say checksum, what it is doing is just it is saying that I will put a value here based on a mathematically or cryptographically calculation of all these like header plus data bytes, and put a value here, so that when I transmit this packet other side, the other side also does the same thing, and the both values should match, and that's what we call checksum match. So somebody, if eavesdropper in between modifies any bit, any field here, then the checksum value will not match, and then packet will be discarded, saying the checksum mismatch, the packet has been corrupted. So that's what we mean by this. And then urgent pointer is just like you're giving a mechanism to TCP protocol where it wants to send some of the data to the receiver, so that it can be received urgently. Like literally it says that okay, this is urgent pointer, so it's like it is a like how many, after how many offsets you can see the data which is marked urgently, and that must be received by the receiver in an urgent manner, and so that a mission critical kind of applications can use this field very much. And TCP options, again, you have like you have different options, like you can see here, like NF option list, no operations, maximum segment size, window scaling, which I say like if you want to use 64K or more than that also, I think it's possible using the window scaling option, where you can have a very big size of window packet. So yeah, there are different form factors where you can have very big window size. Earlier I said it could be a small, I have seen only smaller size, but I'm missing this point. I think like bigger values also have been seen, like in 3G and 4G network, where you have getting a bigger 100 Mbps kind of speed, the window size can be kept much larger. And the selective acknowledgement is again is kind of a congestion mechanism, where you see that how many, like you have TCP source and then TCP receiving end, and how they are uh, like managing all the secrets number and acknowledgement number, and some packets may get missed because of the like unpredictable network behavior, like some may be a high throughput, some may be a low throughput network, and then how to inform to the backend what has been received, what has not been received, using selective acknowledgement. And timestamp anyway, just to make sure that you calculate the round trip timing, and that's what timestamp is used for. And so anyway, I covered all that. So let's go to the next slide right now, and this again about UDP. So UDP will not be covering much, but again it's the same port number concept. Again, U length, you have header length plus the data, and UDP checksum, which again header plus data. So so get this point, UDP does not have a secret number, acknowledgement number kind of field, because it is not a connection oriented protocol, it is a connectionless protocol. It just push data, push identification number, so that it reaches to its destination at least, and it doesn't care what has been received, what has not been received. Okay, but it will keep sending the packet, like keep pumping the data to the other end. Now we again go to IP header. So what is contained in IP header is, if you see, it's source address, destination address, which I say like 2 ports, source port, destination port, source address, destination address, make one tuple, and it's what an operating system keeps as an identifier, so that from this tuple I have this send buffer and receive buffer, so that any packet which comes to this like HTTP server port number 80 or port number FTP 20 for FTP, I will give to the FTP applications, I will give to the HTTP applications. Okay, and then you have other field called time to live, which is again deciding that how many hops that network packet can do into the network, so that it is not an infinite loop. So after a certain time, so this is 8-bit number, like 256 max it can have a value, and this many hops it can have, and then packet is discarded when it is in 0. Protocol is the next level protocol field, and like next level protocol is like layer 4, which is again TCP UDP, and then header checksum again like only IP header checksums, no data checksums calculated here, because all the routers, interim routers which you have seen in the network, like I mean this router, so the router just check this checksum value just for sanctity of IP header, so that it is not modified and not nobody is spoiling with the defined routing of that packet. So that's why header checksum is there, and then your identification field just to identify each and every IP packets, and you have flag and fragment offset, which is again a kind of where you have a bigger packet size and you cannot send over that link because that link has a limited capacity. Then you fragment the packet and you assemble on the other side. So we call it reassemble and assembly. Yeah, fragmentation and assembly, that we call it, and then you provide these parameters so that on what offset each fragments are there, so that they can be reassembled on the other end. Version, internet header length, type of service, total length. So again, total length is the length of IP header plus TCP header plus your data, the complete length. And then type of service is all quality of services that it tries to meet, and so it is again 8-bit number, and you can find Google a lot of articles on type of services. Internet header length is again a like n version, so this is like 4 bit uh, value, and so it's like 4, this value is 4, and then the header length, how much header length is this one, so you might adjust when you get rest of the length. So again you see IPv4 header and this IPv6 header, which like is the next level of IP protocol. And you see again you have version which is 6, traffic class, you have another quality of service kind of field here, and you have flow label. So in IPv6 you will see like each and every packet can be given a flow label here, and then you have payload length, same as here, like you have header length plus this the length of the complete data. Then your next header can be this many headers, so you can see you can have, it can be IPv6 headers, hop options header, destination headers, routing headers, fragment headers, authentication headers, encapsulating destination and upper layer headers. So these many headers, these many fields can be added beside this header part, main header part, and then you can see source address and destination address, which are 128-bit. Yet it's like here is 32-bit, here it is 128, 4 times of this one. So this is what you will have IPv4 and IPv6. Let's next go to the next slide. So now you will see a concept of MTU. So concept of an MTU is like maximum transfer unit, which is defining a how like what is the capacity of data link layer. So like if data link layer is Ethernet, then this is the limit of each packet which this data link layer can pass to the physical layer, and then physical layer can transmit over the wire, or if it is Wi-Fi, then over the wireless link. So you see Ethernet header itself is a 14-byte, which is like 6 source MAC and destination MAC. Again next addressing mechanism at layer 2, and then 2 byte is for identifying which is whether it's IP header or ARP header or something else, and then you have TCP header and then payload. So you can see it is like 1500 bytes, and then 1514, and then 4 byte. That's FCS is again a kind of providing a sanctity to this whole payload, and then it is a 4-byte value. So again this becomes 1518 bytes. So complete MTU size is 1518 bytes. Ethernet MTU is, that's what they call it, different acronyms here, like IPMTU is this, and uses TCP MSS maximum segment size. That's what you call this payload data. As we'll see, TCP has this kind of options that how much TCP MSS can be. It can be less than this also. Okay, but if packet size are bigger than, suppose you have 10k of packet and it is just 1.5k or what you can see in one data link frame, then you need to fragment the packet in 8 multiple chunks, approximate 8 multiple chunks, and transmit over the network, and then reassemble on the other end using the fragment offset and flags fields. Okay. How packet encapsulation works? So if you see like packet encapsulation, also I'll try to explain what happens when packets are received. So you can see in this diagram, like as like you have HTTP data, like you are making a client request, or suppose you have server data, server is sending the packet, and then what you do is like you put a TCP or UDP header here, like with DNS, that it will put like here you'll have URL name and like the kind of question you're going to ask. Okay, I want to make a query, and then you'll be putting a UDP header here on port number 53 for DNS, and then IP header you'll be appending to the DNS server, and then you will be putting a frame header of your next level gateway, which you'll understand that when a host wants to go to a certain destination, it has to look at its next level gateway and get the MAC address of that gateway, so that on Ethernet link or a wireless LAN, the packet can flow from this machine to that machine, which will ultimately pass to its next level gateway, and this way it will lead to its destination called DNS server in this example. And you will see all how the headers are being prepended out here, and when packets are being received, each header is taken out and then ultimate data is given back to the application layer. So that's the way the networking or TCP/IP model works, and you can see a bit more detailed that what happens when a packet is received is like you have a network card and like Ethernet layer, Ethernet NIC card, or wireless LAN card, wireless NIC, and packets are received. So every NIC card or wireless LAN have a mechanism where they don't want to disturb the CPU much time, so they will use a DMA, like direct memory access mechanism, to transmit all the packets to a kernel buffer queue, which will be like a socket buffer to the receive queue, and like a kind of interrupt happens on the device and for each packet, and packet gets placed into a socket buffer receive queue, and where it is actually given to IP layer and TCP layer where the headers are taken out, and in the data in the TCP field we see the what's port number and we identify the socket, and based on socket we take the message buffer and we pass it to the application space. That's how it works, and you need to understand the software interrupt and how to interrupt there's operating systems specific technologies where hardware interrupts are like quick and software interrupts are like something you can delay as an operation, so that what happens here is like in a delayed mechanism the protocols the packets are handled, but as a part of quick response the packets are taken back and put in a buffer queue. The next header comes and I can put it back into the next buffer queue. Like this mechanism goes very fast. And this what I wanted to show you, that it is a client-side programming. When I connect happens, then sync connect is going to happen if the server has accepted your connection. Otherwise you will see a reset happening out here. Okay, so with this I close on the first phase 1 on TCP/IP socket programming, and I'll be covering phase 2 in my next video. Thank you.